let's talk about just waves in general, okay? So, waves. So I guess the first thing we should mention is what a wave is, or what we consider a wave to be, and that is a transfer of energy. Okay, and there's two types of waves that we're gonna be interested in. Type 1, mechanical waves. These are the kind of, I guess, waves that we're used to. I mean, they're in a medium, right? So they require a physical medium. These would be, water waves, for example, or like, waves in a rope or a string. And there's also electromagnetic waves, which propagate through vacuum or through media, and are a little harder to explain, but basically electromagnetic waves are, exactly how to put this. Let's do examples. Examples of things that are electromagnetic waves. So microwaves, visible light, radio waves, gamma rays. Yeah, essentially you're right. The only difference between, say, microwaves and gamma rays, well, is the amount of energy they carry, and that has to do with what their frequency is. These, in a vacuum, these all travel at c, which is the speed of light. That's right. Travel at c, which is what we call the speed of light. Often. And its value is just slightly less than 3.0 times 10 to the 8 meters per second. Okay, it's sort of a nice round number that we can use. All right, so I just kind of brought in a spectrum here just to kind of help you understand that it's, one thing blends into another, kind of like I guess if you want the colors of the rainbow, right? These actually just represent the frequencies, and it just so happens that our eyes have evolved to be able to detect electromagnetic radiation within this spectrum, within this band, I guess. And that's got to do actually with where the sun tends to emit electromagnetic radiation. It emits strongly in the visible region, and we've obviously, come into being on the Earth, and so it makes sense that our eyes would kind of tune into this. We'll talk a little bit more about that later, but this is sort of the whole spectrum. Is there an end to it? I don't know. I guess there's the highest level gamma rays that have been detected, and is it possible that there's higher level ones? Sure. Where do they come from? Where do, these would be considered cosmic rays come from? Well, it's a good question. I think probably not so much that, but more things like supernovas or massive, celestial events, possibly even some that are not well understood at this point. They detect gamma ray bursts and stuff like that every once in a while. And our sun just naturally emits higher energy radiation just through its natural processes. People often panic about the microwave, but if you look, the microwave energy it's considered non-ionizing, if you want. It can't, yeah, well, it's also, yes, but it can't ionize normal matter. Only higher UV and X-ray and beyond can cause ionization, and that's where like your cellular damage would come in. This is the kind of radiation you want to limit your exposure to. Okay. Now we're not going to talk about this too much more for now. It'll come up later, but we're going to specifically focus on mechanical waves. So let's do it. Too hot? All right, so again, mechanical waves are waves that are traveling within some sort of medium. And I think the first thing we should do is mention that there's two kinds of mechanical waves. Actually, before we even do that, these are also called traveling waves. It seems that the textbook uses the term traveling waves quite often, so we'll just call them traveling waves. So again, these are a transfer of energy, one point to another. And there's sort of two main types of mechanical traveling wave. So what makes them mechanical is that they can't pass through a vacuum. They can only pass through a physical object of some sort. So we'll start off with, let's put a null point or a resting point of a medium. And I can't do that. Okay. And okay, so this will represent, let's say it's a rope or a piece of elastic or like a slinky or something like that, and it's laying on the ground and you're looking down at it. And this is its resting position. And you have one person on each end of the slinky, or you could even have this, you know, fixed to the wall or something like that. And you could have someone kind of at this end holding on to it. Okay. And what this person's going to do is they're going to whip the slinky away from its resting position. Well, what that'll do is it will create, I'm going to draw a full wave here, a wave pulse. Okay. There's different kinds of wave pulses. This is like a full wavelength wave pulse. You could also do like a single wave pulse like this, and that pulse will have a velocity along the medium. Okay? We're just going to label the parts of this here as we go. So the displacement from the null point or resting point of the medium has a name, and that is the amplitude. This is also an amplitude. Okay. If we're looking at this from the side, this is often called a crest. This comes from like water, yes, and a trough. And the other big thing to note here is does not look very good like that, is the wavelength, is the distance from equivalent points in the wave. Can I draw a straight line? There we go. And this is wavelength. And there's a symbol for wavelength that is lambda. Okay, so what else do we need to say about this? Okay, well, I think we've pretty much covered the major parts here. Again, I'll just talk about how this is a pulse. Now, if you sort of continue to oscillate this thing, right, you get kind of a continuation. Sometimes it's a little bit easier with wavelength to realize that it's, you know, either crest to crest or trough to trough. Yeah. chop. So that's also considered to be a wavelength. And this would be one oscillation of the wave, right? So from start point, media up, down, and back to resting point. Something to notice though is that if you're looking at one point on here, as this wave comes by, well, at least the way this is set up, if we start from here, your medium will move down, up, and then down again, right? None of the actual material is passed along the wave, right? Right, just the energy moves through, lifts it up, down, and back to its resting position. So that's something that maybe is a little confusing or something, but there is no net transfer of medium. No, not even with sound. It makes it move like a longitudinal wave would move. Yes, that's right. Yes, yes. So there's no net transfer of medium. And one other thing to note is that the velocity of the wave is dependent on the state of the medium. So, in other words, waves travel at a set speed for a given medium. If this were like a guitar string or a spring, if the tension is kept constant, the velocity of the waves will stay constant. Okay, even if the amplitude is reduced, right? You have a lower amplitude, which means that the person's putting, if you want less energy in per unit time, the velocity will stay the same. Okay, so the velocity is set by the medium. The other things can change. Frequency can change, wavelength can change, but velocity is set by the medium. Okay. Let's talk about a longitudinal wave. These are a little bit harder to kind of draw, but I think maybe one way is to use a spring. So I'm going to try to draw a spring. Okay, so we might have a coil spring like this, and we might have a spot where we have a wave coming through it. Don't worry, I'm gonna, yes, label what we're doing here. So, okay, so we have this, and we have this. The C part is a compression. The R part is a rarefaction. So how you'd get something like this is if we're back to our spring example. If you say you took your hand, you can draw a hand here, or your finger, and you pull the wave back towards you and release it, like you spring it. Makes a spring noise. Boing. Okay? You spring it. You compress and rarefy, and there could be another one up here. I'm not exactly sure how we have this, but I guess the rarefaction could come first. Correct, right? So here's your resting medium, right? I try to draw these all sort of equal distance. This is your compression, and then your rarefaction, yes, is spread out more. So if you were to pull this back and release it, you'd rarefy in front and compress behind, and then that spring would go the length of the... So this also has a velocity, right? This also has a wavelength. It has an amplitude, which is a little bit harder to kind of define. Yeah, you could have more or less compression and rarefaction. It's a little bit different than amplitude in terms of your transverse wave, and I forgot to actually mention that. So, names of the types. This is called a transverse wave. And the thing about a transverse wave, just maybe make a note of this, is that the medium is displaced perpendicular. I'm just going to use this symbol for perpendicular to velocity direction or wave travel direction. Right? So the medium moves perpendicular, the wave moves along the medium like that. Okay? So just maybe put that in. And we should probably label this as well. This type of wave up here, it's called a transverse wave. I don't speak Latin, but trans usually means across, right? Or something to do with across. So it sort of makes sense, okay, my medium is getting displaced across from the velocity of the wave. So it sort of describes it. And then this type of wave is called a longitudinal wave. Longitudinal wave. Okay, and the medium is displaced parallel to the direction of velocity.